But if we want to build a really intelligent machine, we need to go on further like that. We need to have a machine that is able to predict what will happen in the future, right? So if I happen to drop my glass, I will know that it will fall down and crash into the floor if the machine doesn't know that. And something more that is also very important is to detect events that are surprising to me. So say we have this speech-to-text system, it should be able to detect, oh, I don't know this word, I should maybe adjust my model to include this word for the next time. Right. So what is a generative model? Well, that's very simple because most of you actually know it. This is a mixture of Gaussians, which basically models the density over your data input, right? So that is the generative model. It models the density over data. It doesn't, like you can have, for example, the data and the label, but that doesn't necessarily have to be so. So you can basically model the density over all images. And then once you have that, you can draw samples from this density, which means you can draw different images that have never existed before. One thing that is very important for these things is that they capture the uncertainty that we have over our data. So, for example, if we see the image of a cat but have never ever seen a cat before, our model should say, hey, I'm very uncertain about what this is. But usually we'll say it's a dog, right? Okay, cool. So let's go into detail. Why do we want to have generative models in the first place? Well, first of all, we have this part, which is the product side. Here we have text-to-speech, which would exactly be the synthesizing step that we were talking about before. Say you have a model that actually can take any text in Swedish and generate the speech that fits that text, right? Then you could train your other model to get the text out again. Another very important application is science. For example, drug discovery, where you can generate the molecule structure of different drugs and test it automatically online instead of having to go into the lab and trying each of them independently. And then something that is very close to what I'm working with is to actually generate data in order to be able to interact with the world. So say you have a robot that is supposed to learn how to manipulate an object. It would be super good if it had this generative model that could predict what would happen with the object if it applied some certain action to this object, right? So this is, for me at least, the most important part, but I guess other people might have other things about this. Right, so here we see some very, very early examples from 3 years ago on image generation. And I think it still more or less looks like this. So if you read a paper on deep generative models and you see samples drawn from this data distribution we learned, they all look kind of sensible, but mostly they are printed in such a small format that you can't see that there's nothing on this image. But that's just my opinion. So sure, it's super. You're super good at like producing nice images of faces because they're easy. But if you want to have something that models more, it's. I'm not so sure about this.
Or what are they trained on?
See, I didn't make the slides, so I don't know.
That's fine.
I would say this is Cypher,
yeah,
right?
okay,
Because the images are so small, or maybe tiny ImageNet.
Yeah.
But
yes.
sorry, isn't that also due to the processing? Because if you want to generate a massive picture,
I don't think so. I think these things pick up on the local statistics, and then they produce local statistics that look coherent. But for us, the global semantics are not there in the images. Right. Okay. So something cooler is this one, where they first predict how the pixels could move, and then they produce the video that fits. But you see that, yeah, it's not pretty. It's what I said. It doesn't think about the global statistics. It just looks at the local statistics, right? But you see that it basically, from one image, it can generate different videos of the future, which is pretty cool. Yeah. Okay, cool. Right, Then another thing is that you want to be able to generalize from as few examples as possible, right? So this is a paper that looked at one-shot generalization, where they get an alphabet, which is at the top there. That's what the model sees, and then it's able to generate all of these samples from that alphabet without ever having seen any of these. So that's pretty cool, which means basically it has learned to generalize the density it has learned on other alphabets to a new alphabet. Okay, right. This is another example where we, once we have learned how to generate data, can use the features that are in the model to manipulate the data as we want. So there's one dimension that manipulates the scale, at least they say so. Yeah, this might be a bit smaller. And this is the rotation of this object. And down here they have one dimension that basically manipulates this pedal down here, and this one is how many bricks there are. Right. So all of these things are pretty cool, right? How do we get there? So we first start to talk about probabilistic deep learning. Of course, we all know deep learning, and we maybe know probabilistic reasoning as well. We know that deep learning is awesome because you have rich models, and if you have a lot of data, it scales nicely, right? And you can basically just pip and stalker us, and then you plug and play all of these nice layers, and you get something awesome out. The problem with this is that you never really know how good it learns, and also that you only get out point estimates. So instead of like modeling the whole density, you only get one single point for one input point. Probabilistic reasoning, on the other hand, is very nice if you look down here, because it unifies all of this, that you build a model, you have priors on your parameters, you know how uncertain you are, you have uncertainties over your predictions, and so on, and it's super robust. The problem is that in the old days, you only could have either like linear models or models with priors that fit your posterior, for example. Right. So this is tough. Therefore, it would be super nice to take both of these, put them together, and get something awesome out. Right? So let's try. We have on the top of our machine learning universe the algorithms. These are any kind of machine learning algorithms. And the two columns, pillars that hold this roof, are the models and the learning principles of these models. So what kind of models are we thinking about? Well, either we can have fully observed models. For example, you have your classifier where you put in your input data and you know your output data, right? Everything is nicely observed. Or you have latent variable models where you have one variable that you have never observed, and this is what you have observed. So say in the image case, for example, this is your image of this cube. These are the different parameters of how you can manipulate this cube. So one of them says how big it is, one of them says how it rotates, and so on. And we can distinguish, in this case, between two different things. So one is where we have a likelihood. We define the likelihood of this x parameter, which would be the Variational Autoencoders. And then we have the Generative Adversarial Network case, the GAN case, where we don't know what the form of this actual likelihood is. We just have something that says, yeah, it might be close to what I wanted to learn. Okay, right. So we are going to look into both of these, mostly into the Variational Autoencoders though. Yes?
Right, so the difference is that here that on the top, x is something you have observed, and then f is something that you're trying to predict, and in the bottom you have that c is never observed.
Exactly, exactly. You can only try to infer what z has been given that you have observed your data. Okay, cool. So let's try to build a normal generative model without, and is this moving? Okay. Without any like neural network stuff. So we start out with the z. which we say is a normal distribution, like a standard normal distribution. And then we have another unknown parameter up here, the theta, which basically are all the parameters in our model. So we sample both this z, which actually determines the form of the x, and we sample the thetas. Put these into this Gaussian, where we say this x is equal to one of the thetas plus whatever we sampled here times another theta, and then the variance is also a theta. Right, and then if we want to sample from this, it's basically sample, 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 and we have generated a sample. Awesome, right? The problem is that we don't know the thetas, we don't know the z's, we only have the x's, so we don't know how to sample such that we get x's out that look like the data that we have. Right. Therefore, we need some kind of learning principle. Here is a long list. You might know this one, and that one, and that one, and maybe some others. I don't know, but today we're going to talk about these, the variation methods, which do sometimes they look super scary, but I think I try to get out the essence so that you can understand what we're doing. Right, so let's try to talk about approximate inference then. What do we need it for? Since I didn't make these slides, I'm not super happy with this. I would say prediction, yes. Given that you have seen the past, you want to infer what happens next. And then the parameter estimation as well. Given that you have observed your data, you want to infer what the thetas were. But then one thing that is missing is you want to infer the latent variables, right? You want to infer the z's. And that is what we're going to talk about now. So I don't understand why it's not on this slide. All right. So now starts the math. We have our x's, that's the data. And we also want to have z's, which are the latent variables. So each data point has been generated by one of these latent variables. We don't have access to these latent variables, right? So if we want to compute the data log likelihood, we basically need to integrate over all of the latent variables that could have generated this data in order to get here. And if we have done that, then we could compute the best theta that actually would explain our data. Right. However, we don't have access to this or that. We only have access to the data that we actually sampled up there, right? So we only have access to this and can try to maximize the data likelihood. For that, we don't have the integral, we just have the sum over all of our data points.
Sorry, can you explain that difference
yes.
again? What is the difference between the x's and the
right.
data?
So yeah, sure, that's not the best. So x in this case is random variable. This in this case is just a set of data points. So okay. This is the continuous case when we actually have everything. This is the approximated case.
Discrete. Discrete.
Yes. Yeah. So now, in order to do all of this computation, what we actually need is the posterior. Can you see this? Yeah. E of z given x. So we would actually, given for each data point, we would like to know the form of the z, right? So let's try to find that then. This is the form of our true posterior. This is p of z given y, but it's actually an x, as you can see here. And we want to approximate it. But we don't know the form of this, so we will just say we want to find a simple distribution that is close to what this one looks like. So we have a bunch of approximation classes, mostly it's Gaussians, as you can see here. And now we would like to find the one distribution that looks as close as possible to this one. And for that, we want to minimize the KL divergence. Who of you knows the KL divergence? 1, 2, some people. Okay. So this is basically a measure between probability distributions. So say you have a Gaussian and a Gaussian, then that is a measure between the two means and between the two variances. So if these are overlapping, it should be 0. If they are far apart, it should be far large. Right, okay. So, I would need a pointer. We're interested in finding the posterior up there and want to approximate it by a very simple distribution, which is our Q. So what we really want to do is to minimize this KA divergence that I was talking about before, which has this form. So it basically is more or less an expectation with respect to the approximate distribution, and then it weights the samples that come from this distribution with the real posterior. That's how it measures the distance between the two distributions. Okay, so we all remember our base because we learned it by heart, right? It's very close to our heart, right? Okay, so it's you basically can switch between the conditioned variables by switching them and then weighting with the priors. So if we use this thing here and plug it up in here, then we get the following equation, which is down here, where you just need to basically push this in again and then push the other thing out again. Just do it at home. Okay, right. So now you see that this term here is actually the log likelihood of our data, right? Which we were talking about before. So this is actually what we are interested in. And it does not depend on the z anymore, which means it's not part of this sum, and we can just put it onto the other side and get this onto this side. So suddenly we have an equation of what our data log likelihood looks like in terms of these approximate distributions and our original distribution. This is awesome. Of course, that's exactly what we wanted. What's hard for us is that we can't really compute this one because, as you remember, we didn't have access to this one. So that's tough, but we are lucky and can use a trick by remembering that this is a distance. It's always positive, which means this term, that one, is bounded by this term, and as long as you maximize this one, you will get closer to that one, right? So we just drop that KI divergence and only look onto the second term here. So these were all the Wikipedia equations. Now we come back to the real deal, which is this one, which looks very close to that one. Right. In this equation here, we have substituted that Q thing that you see up there. Now we suddenly have an I here. That means that for each data point, we want to approximate a whole distribution over the latent variable. So say you have observed an image, then you want to approximate a mixture of Gaussians for that image. For the next image, you want to approximate another mixture of Gaussians, right? This is what variational inference looked like until 2014. That's also why it didn't really scale, because you need to do very tough computations to get all of those distributions. Right.
So what are those when you get those distributions?
Yeah. So say in the topic models, right, where you have this document, then you learn a distribution over each of these parameters that you need in order to generate it for each of the documents. So in the case that we had before with the this thing here, Z and then X and then Peter, then in this case we would have to approximate for each of the x's a mu and a sigma for the normal distribution that was in here. So if we have n data points, we have 2 times n parameters that we need to estimate. Independently, yes. Exactly. That's tough. Tough love. Okay. I'm way too slow, but okay. We will get there. Right. So now we have this part here that we can deconstruct into one part that is reconstruction, which is basically the likelihood of the data point given the latent variable, right? And this is the distance between the distribution over the latent variable and some prior. It's basically a regularizer so that it doesn't just do whatever it wants to. Right, so now we come to variational autoencoders, where instead of saying we have one single distribution for each of the z's, we take this and form a function of our input data. So now before we had to learn 2 times n parameters. Now we just say that mu I and sigma I is a function of xi, right? Something like that. So now we just need to learn the parameters of this one independently of how much data we have. Yes?
Could you just go back a slide so that
right.
we'll clear? So in the second equation, we have this inequality. What do we use this inequality for?
Well, we want to get as close to this one as possible. So we just try to push this up as high as possible while optimizing. So then the model gets as close to the real log likelihood as possible.
Okay. And then that, like, so you can do that just by itself, but you can also then go back to some kind of KL divergence.
Right.
In the third equation here.
Yes, right. But this is a different KL divergence compared to that one.
Oh.
Even though it has the same form. So that one is between Q and P of Z given X, and the other one is between Q and P of Z. See, you shouldn't have equations from 2 different sources. Because this we have the form of, right? Because it might just be normal distribution. Okay.
And in general, so we have this model that says this is the probability for a data point, and we want the probability for the data point that we have to be maximized.
Exactly. Yes. Right. So, in principle, this is a variational autoencoder. You have this Q function, which is this function, that takes as an input your image and gives you 2 different parameters, which in this case are the normal distribution parameters. Then you sample from this latent distribution, have another neural network that is the decoder, and it learns to output an image. The way that you train this is by having the log likelihood of this image, of the original image given this prediction, and then you also have the KA divergence between whatever you learn here and a prior that says it should, for example, be a standard normal. Right? The reason that we really need this is because basically if we wouldn't have it, it would set the sigma to something that it doesn't have any variance, for example, because it doesn't like variance in the system. So you need to have some kind of normalizer there. Right, so this is a variational autoencoder. If you have trained it, then you can visualize the Z space. This is the Z space. You can sample from that Z space, push it through the decoder, and get an image out. So this is exactly how generative models work, right? You have model to density, now you can sample from it, and look at what the data looks like. Cool.
Sorry, can we
Yes.
go back a slide? So in this slide, and you showed mu I and sigma I there. Right. You said that we approximate a mu and a sigma for each.
Right, we did that before.
Yes.
Now we have a neural network that does it for us.
Now we just have a single value for mu and sigma.
No, for each image you have a different mu and sigma,
Right.
but you don't need to approximate it. You just need to approximate what the neural network looks like. So say this neural network has 1,000 parameters. You have 1 million data points. Before you had to approximate 2 million parameters. Now it's 1,000. So this is better.
Okay.
Right. Yes.
So in here you have this two-dimensional thing.
Right.
What is it in? Is it two-dimensional in reality?
I don't think so. I think this is scaled down. I think 8 would be the choice. Okay, right. So one problem here is that we need to compute the gradient, but we have random variables in the run, right? That's super noisy, and our gradient will just go up and down because it will scale with the variance of the latent variables. Therefore, we use a very neat trick, which is the reparameterization RE trick. So we simply draw an epsilon from the standard normal distribution. We have learned the mu and the sigma from our neural network, and then we can compute a sample from this normal distribution by just having mu and adding the sigma times this sample. And by doing that, we remove the dependency of the gradient from the z's, and it only depends on the epsilons, which has variance 1, right? So it's nice. And that made these models actually scaled to the size that we have today, that we could use this. Okay, cool. So if we want to code this, it's super easy. You have the input, you have some neural network that is the encoder. From there you get out your mu, and you use a trick where you say this is the log of your sigma. Then you draw your epsilons, you set z equal to mu plus the exponential of that log times the epsilon. You decode this one, and you compute the likelihood and the KL divergence between the prior that we have and our z distribution, and then we train this. So this is all you need for training a variational autoencoder. The reason that we use this trick here is because we want it to be positive, because it's a variance, right? So then it's nice to just use the exponential there. Okay, cool. I will just jump over this, I think. Now we will get to the gun part, where we don't have a likelihood, which means usually we don't have a likelihood. So say you have images. What is the likelihood of an image? Right? Is it the pixels? Is it the thing that is in the image? It's super hard to define, and I think that's why guns are so much more powerful than variational autoencoders in generating nice images, because you don't try to force a likelihood onto the data, you just let it be. Right, so this is called using implicit distributions, which means you use the distribution, but it's implicit, so you don't know the form of it. The way that we produce samples is to sample from some z that we don't really care about. We don't care about the posterior or anything. We just sample from it, then we learn a function that generates our x's. The problem is, how do we know it's a good x? Well, we need someone that says the x generated from our model is close to the x's that were in our data. That's what the gun does. So we have different methods that we can use here. Some of them are more used, some of them are less used, but it's basically either you compute the difference between the two distributions, or you compute the ratio between the two distributions, and then you try to minimize these in order to get as close to your data distribution as possible. Right.
Why not callback library?
Why not?
Why not callback library?